Welcome everyone. We're going to start today's seminar, the first of this week's seminar, as we have an extra seminar tomorrow as well, which you are all more than encouraged to come to. We have with us Millarca Valenzuela Picón. She's a geologist and doctor in sciences, expert in meteorites. She's actually an academic at the Department of Geological Science at the Universidad Católica del Norte in Antofagasta, Chile, and a researcher at the Centro de Astrofísica y Tecnologías Afines, CATA, and the Instituto Milenio de Astrofísica, MAS. The asteroid 11819 has her name after her contributions in the fields of meteoritics in Chile, South America, and Latin America. She is an author alongside Gabriel León of the book Meteorites, Stories Between the Sky and the Ground, published in 2024. And well, we're really excited to hear your talk.
Hi, everybody. I'm very glad to be here. I'm very happy to have found the time to arrive here, also with my PhD student, Kevin, that he will stay for longer, 2 months. ¿Hay un acoplado, parece? ¿Puede ser algo? Hola, hola, ¿habla bien? ¿Sí? Okay, so here I show some of the most important symbols of my region, Antofagasta, that it's where it's the most the core of the Atacama Desert, the arid zone, the most hyper-arid zone, probably of the world. So we have Paranal Observatory doing all the research related with astronomy, ALMA as well, looking for the answers for life, for the planet formation, and well, the hen of the desert saying, welcome everybody. So I know that some of you have been working in this region, so it's a very good opportunity, this environment, to learn a lot about life. We have been working in meteorites, I think, more than 20 years. I was the first one to take this challenge. There was, of course, Chile is very well known by the earthquakes, like tectonic activity, the Andes Mountain, the volcanic activity, the mining deposits. So for a geologist to born or became a geologist in Chile is very difficult for other kind of science. So for me, it was really challenging to get into something that was nobody to teach me. So I have been in this work for 20 years, but now I always thought I don't want to be like an anecdotic history or story about, a girl that studied meteorites. So now I can say that it's a proper line of research, very, very young yet, but with at least 2 PhD researchers, and now coming the next generation of PhD students. So what we do, it's mainly to study meteorites, but also we study impact processes, because we have one impact crater also in this region, in Antofagasta region, that I will speak later. And also just some approaches to planetary science that make in my geological community, I am like the outlier, and I haven't been able to generate strong collaborations with them. But the astronomers have been very keen to give me a space in their community because of the importance of the study of meteorites to understand some questions related with planetary formation and origin of life and this. So for that side, it's that they, after this CATA institution that I will speak a little about that. It's a government funds for big projects that are funded for 10 years. And in this case, CATA 1 already finished like 5 years ago. And now we are in the second 10 years project. So it's the only way to create new lines of research. So the first CATA for the first time put exoplanets as a goal to develop that. And now it's a big community of exoplanet astronomers. Keep going, keep growing. And for this CATA 2, so these 10 years that start 4 years ago, they proposed to open the line of astrobiology as a formal research line, because until the moment it was just people doing certain things but not coordinated. So for that reason, it's the first time they invite a geologist, and also, well, the first one to arrive to this group was a geologist. And being there, I say, I really need a biologist also. How we will be doing astrobiology without a biologist? So now we are also a geologist and a biologist. And we have been studying for a long time the flux of extraterrestrial material studied from the desert. And doing a lot of the most basic work in the chain of studies of meteorites. That means to go to the desert, to do these field works in a systematic way, to rise up the statistic of the meteorites that we found in the desert. So we are very focused in do expeditions. We try to do at least one big expedition of 2 weeks. But when we have more funds, we can do more. Meteorites, we do chemical characterization, petrological characterization using different techniques I will show after. Also some spectroscopic characterization, like near infrared, Mossbauer and Raman. And the impact processes, we have been also finding, just because we are in the desert walking, we have been able to find, in a serendipitous way, new discoveries, like this new tektite field called Atacama, also in the region of Antofagasta, that we haven't found yet the source crater. And study, of course, the impact materials and things related with that. So my presentation, I will be looking for this different aspect that has our region to study. And well, astrobiology, that not in my case, I haven't been yet involved in extremophile work, but my colleague Cristina Dorador do. But now with Kevin and also with Camila, my other PhD students, we are going to, with Camila, look for the colonization of microorganisms in chondrites. And Kevin will be looking for also organic component in carbonaceous chondrites. So these are what we see, like a really a big opportunity to make grow astrobiology in Chile, because we have detected that we have different groups working in different places in the whole Chile, universities, the Geological Survey, mainly, and the Antarctic Chilean Institute as well. So Antarctica is a target as well for these expeditions. And all the Atacama that has not been completely studied. So my background is geology in the Universidad de Chile. And when I became geologist, I decided to not continue. I finished doing a thesis about one meteorite. but I discovered that I was the only one, so I didn't continue. Went to work in the industry, and being there, I received an email saying that a Canadian group needs help for somebody that knows about meteorites to study the impact crater, the Monturaqui impact crater. And they washed my brain saying that even if I don't have anybody to be guide, I should go through this process. So I get into the PhD. And it was very difficult in the beginning, but after I could create collaborations with people that was very interested to study the Atacama Desert meteorite that were very scarce in that moment. So from 2005, with the Natural History Museum in London, we made the first expedition, but was very like a chaotic way of look, not really. It was just in case if we find something. But in 2006, I start a formal collaboration with France, with the CEREC. And from there, we have been like 20 expeditions from that time to now, looking. So the first ones were just 3 meteorites after 2 weeks. But in 2008, I think that we are more. All the time, we were only 3 looking for meteorites. After we start to rent 2 cars, and after we arrived to 5 cars. 2017, I think it was the one that was more people looking for meteorites, around 20. And so this has made a big impact in the science we have been doing. So before I continue with that, so I want to show you a little about. So what I was telling about CATA, so it's this big project that Chilean science rely in this fund to make grow. It's very little the amount of money that it's invest in science in Chile, so it's very difficult to start being a scientist and continue the scientific career because it's really hard. And this kind of works has helped. For that reason, I think to be in connection with the astronomy community that has make a big effort to make grow astronomy has been so successful. So now we have a lot of telescope that people from all over the world comes to Chile and to the north of Chile to use them. And that trade has been very good to create more schools of astronomy and trigger this expansion of other subjects. So that it's our last annual meeting, because we come from different universities from all Chile. I think I'm there. I don't know how to do that one. And Kevin is here. That is Kevin. Hola, Kevin. So it's a very active community and covers different subjects related with evolution of the universe, theoretical astrophysics, galaxies, star formation, black holes, the local universe, and planet formation. That we are mixed with we are part of the group of exoplanets and meteorite in astrobiology, where meteorites is there. So that our directives, Patricia Tisera, the 3 of them are astronomers, Roberto Acef and Elise Servagin. These are the different groups. So here is our group, exoplanets and astrobiology. And James Jenkins and Dante Miniti are the PIs. So that is our group. So most of them are doing exoplanets. So me, it's the geologist, and Cristina Dorador is the biologist. And we have also Cesar that it's doing solar system study, objects in the trans-Neptunian objects and similar things. And in the carrera, in the Departamento de Ciencias Geológicas, we have the Carrera de Geología, the master program, and also the PhD program. So in the geology department, we are like 14 professors for 400 students. So it's one of the biggest schools of geology in Chile. And as we are in the Atacama, so most of the students come with a fixed idea to be rich being a geologist because of the mining companies. So for this kind of scientific areas, it's very difficult to get them involved in this kind of studies. So it's an effort to try to bring them to these subjects. And in the PhD, we have 3 lines of research with endogenous processes, exogenous processes, all related with the things that we can find in the Atacama Desert and the Andes. And also something that may be interesting, it's the geobiology line that has been very focused to study salars and other environment in the present, but that I think has a big potential to generate new theses related with some things that are more related with astrobiology. So that I mentioned because my idea to be here is to try to potence the interactions of our people with you, because you are a referent for us, how you have created this Center of Astrobiology and the different groups that are working here. I come back. So that was part of my PhD thesis. In that time, 2005, it was a publication from some researchers of the Europlanet mission or something to Atacama, with a paper saying that Atacama was the worst place to find meteorites because most of the rocks looks like meteorites. So it was an horrible, so I was in the first year of my PhD, I said, no. And so I just stick to go to look for meteorites in the places that we already know that people found meteorites. So in the second or third time that we went there, I said to my colleague, my French colleague, just take the car and let's go to explore somewhere how it can be so difficult to find meteorites. So that was the discovery of the San Juan area. And that was the initial. So in this case, we walk this area, it's a kilometer. So it's a very little space where we found many different meteorites. So we found that at least 9 to 12 different meteorites were there in a square kilometer. And the abundance for the other hot deserts was less than 1 meteorite per square kilometer. So when the big boss saw that, say, okay, I pay for the other car and we go to look for all the other surfaces. So that was part of the PhD. The discovery of this, I was just studying the weathering processes on the meteorites that I received from the private collectors. But I could include all the new findings that we did in San Juan, and that was like a promise that if we go and look for other surface, it will be as good or better than this. So in the meantime, with this idea that this could grow in Chile, I start to use my funds of the postdoc to train new students in the whole Chile. So I did a big call for any geology student that likes meteorites, because we are very few, and I was not happy just doing for one institution, so I opened it to everybody, and we get like 25 people in the beginning, and from this group, at least 3 or 4 continues this way. So it was a very good initiative to promote this and not stay just as a lonely researcher. So I create this group, the Grupo de Meteoritos en Ciencias Planetarias in the Geological Society. And from, I think, I don't know, from 2016, it's working, and it's still like a place where we can found new potential people that will dedicate to meteorites of planetary science. So the Atacama Desert, as you know, has this incredible configuration that has in the Pacific Ocean, with a Humboldt current making it very cold, high pressure, not so many clouds, and also the Cordillera de los Andes in the other side. So it creates a rain shadow effect that makes this area of the Pampas a very special area for astrobiology, because of the hyperaridity that has been there for, well, the onset of the Atacama Desert as a desert is 25 million years, with difference in the different areas. But we can see that there is places that the water is almost absent at all. So it's very like similar to Mars in many ways to understand processes. That it's a statistic of how we start just finding 3 meteorites in 2000, that is 5, after 3, after the 21 in San Juan, and after the boss start to pay more for the cars. So we start in 2011 to get more than 200 fragments in these expeditions. And in the 2017, that it's not here, we found 600 fragments. So it's a lot of work. For that reason, we don't do the thin sections for everyone. We just do the polished sections. And after we decide to who will put more effort to analyze, because as I said, we are like the hard work of meteorites. So we go to the desert, and after we need to classify. And this kind of amount, well, most of them go to France, because in Chile, I was the only one. I was not attached to any institution. So most of the meteorites went in the collection of CEREC. But with the idea to grow this in Chile and create a proper repository and more researchers doing the classification. So that is the big group of 2017. Many French, Chileans, and invited people. And we do systematical search, that it's to go 10 meters each other, separate, following a direction, very concentrate, kind of meditation state. This area is amazing because it has a perfect contrast, but it's not the common scenario. And until September of this year, in the meteoritical bulletin were more than 4,000 official meteorites that are the ones that have been classified and have been okay for them. But there is still waiting a lot of meteorites to be classified. So the number probably it's around 5,000. And from that, we can see the distribution of the different types of meteorites. So in the beginning, we just have irons and ordinary chondrites. But as these expeditions were improving the numbers, we could start to look like the world statistic for meteorites, that it's mainly comes from the Antarctic expeditions. So that are the different types. So It was incredible to find, well, now 51 carbonaceous chondrite, enstatite, there is one rumuruti, a lot of irons that were the first one discovered, 2 palacites, 24 mesosideриtes, and from the achondrites also we have eucrites, diogenites, ureliites, acapulcoite, howardites, and 1 Martian meteorite as well. Most of them founded by other expeditions or even just tourists that has found the meteorite. The Martian meteorite was French tourists that found it, and they ran away with the with the meteorite. So we haven't seen yet, but it's an important meteorite that it's is showing something important about the presence of water in Mars. So there is some Caleta el Cobre, ¿cuántos? Caleta el Cobre is the name of the meteorite. I don't remember the number, but there is many publications about this meteorite. And so the most we do is the study of this meteorite flux at the scale of the window that the meteorites in the desert give us, that it's from million for 1,000 years to million years. And it's very important then for this statistic to construct, to do this systematic way to find them. The collectors, the private collectors go in big cars in this fast speed, and they found just the big ones, and they lose all the little ones. So just walking, we can find things very little and estimate which are the distribution of mass of the samples that arrive to Earth. And to know how much time they have been there, it's very important also to date the terrestrial age, that it's very expensive, so we don't do it to all the meteorites. We do a selection of these subsamples, and with that we can characterize different surfaces. So that are the statistics of meteorites around the world. And here are the number of meteorites. You can see that the most of them are in Antarctica and the Sahara Desert. And it's growing the amount in Atacama Desert. And of course, it's different, the processes that occur in Antarctica, because they fall and they move with the ice and go and appear in the foots of the hills because of this erosion that create the winds. That is very different from finding the meteorites that are in the position where they fall. So we need to walk a lot. And in most of the desert, it's less than 1 meteorite per square kilometer. So it's very low probability that somebody that wants to find a meteorite find really a meteorite. So that is how it looks. Atacama, with very little rain. Something that we look, it's places where we can see that the wind has blown all the little particles. So we love ventifacts. So we try to follow ventifacts to found these very nice areas with deflation, like this one that creates also the pavement of the desert. That is an amazing ventifact. So these deflation surfaces are the best to try to find meteorites. So we found very few per person per day because, as this paper in 2005 said, most of the rocks looks like meteorites. So you see, this is not like the first one I show you. These are the reality of most of the surfaces that looks very similar to meteorites in color. So it's thousands to millions of rock for 1 meteorite. So just a quick, so you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So choose which is the meteorite. 1, 2, 3. Let's check if you were right. So that it's the meteorite. So it really can look very similar to dacitas, rhyolites, and other volcanic rocks. So it's really something that you have to learn in the field. So that is how we do the search. We need to do after classification. And because this can be, here I have something. So this is how it looks, the search. So this vast, we walk like a 1 kilometer, going to one side, and after we come back, we do like a, so what I was saying is that only this walking very slow makes us possible to find these things that are less than 10 grams. That is where the distribution of mass goes to these little fragments than the big ones. So we have this bias done by the collectors for many years that were always something more than 1 kilogram. And in these little ones is where we have found these very diverse different compositions, different types of meteorites. And the pairing, it's something that it's not trivial because the number of stones, so we can find 600 meteorites in an expedition, but some of them will be from the same fault. So we need to try to see all the characteristics. So it can be atmospheric fragmentation, but also terrestrial fragmentation. So we need to take all the coordinates and things. We analyze a lot of data to try to get to these different criteria of pairing, like the classification of the meteorite. Very important, the magnetic susceptibility. And the terrestrial age when we can make that datation. So some of the works that we have been doing, this was related with my PhD, the San Juan meteorite field. After comes other PhD student, a French PhD student, that we were working in El Médano, and my numbers were very little, 12 meteorites per square kilometer. Aurora area was 147 meteorites, different meteorites per square kilometer. So that was the cover of the meteoritics and planetary science of that year. And I was very happy, but also very worried, because once you put that information in a journal, next year will be everybody there. So, and that happened. We could see how was the increment of people arriving to the Atacama Desert after 2017. And now it's a very, very bad problem that we have. We strengthen the efforts to try to make a protection for meteorites. But as meteorites are rocks, and Chile, it's a rock exploding country, it was very difficult to make them realize the importance and the urgency to do it now. So we are still doing that. In 2019, also, we could see other surfaces, and found that the average age was of these terrestrial ages of meteorites were 700,000 years, where other hot desert, it's only 12,000 years, and Antarctica, it's 99,000 years. So it's one of the oldest meteorites that we can find. It's in Atacama. And this one, it's from 2025, that we found this Catalina dense collection. So we have been like moving during the years in different areas. In Catalina, we found a lot of meteorites. In this work, we analyzed almost 1,600 meteorites. That brings a density of 2,235 meters per square kilometer, and the little pieces and everything after pairing, and 67 meters per square kilometer, bigger than 20 grams. So in that Catalina area, it's the bedrock. It's ignimbrite. So it's very easy to spot the meteorites, and it's very difficult to walk the line because you go walking and somebody says, stop. So everybody stop when somebody found a meteorite. We take the coordinates, we do all the picture, everything. So Catalina was a nightmare because everybody, not even 2 or 3 minutes, would say, stop, stop, stop. So finally, we found this huge amount of meteorites in many years. So this is the compilation of that we found in at least, I think, like 4 campaigns. With the mass, it's so this is the mass is there. And the magnetic susceptibility is the colors, so we could see easily the types of meteorites that could be there, displayed there. And these are only the ones that are more than 20 grams. So it's also more easy to see the tendencies of something that we can check if it's pair meteorites or not. So in this way, this image shows the meteorites that we could found that were clustered. So in the different types of ordinary chondrites, H, LL, or L. And see also the mass distribution of the meteorites, that in this case is the crosses here, these ones, against other desert dense collection areas, like the blue one, El Médano. The green one is Antarctica. And also something important that we study is the weathering. So how the meteorite react with the environment, and how quickly or not quickly they change the composition to things that are more stable, like oxyhydroxide of iron, because all the minerals in the meteorites have iron as iron 2 plus or iron 0. So all the iron 3 plus, we can correlate it with the alteration products. So for that reason, we use Mossbauer sometimes to study the weathering. So here is the Sahara for comparison, and Oman. So Oman has a double B3, so it's more weathered than the collection of the Catalina area and also the Sahara meteorites. And well, here is the work of Drouard in 2024. And we have then the difference, so that it's plotting the terrestrial ages with the normalized cumulative frequency between Atacama, Antarctica, and other hot deserts. And we can see how the Atacama meteorites really go to more older ages. So, and this is a close-up of these two, the Antarctica and hot desert. So it's a really unique type of sample that we can find in Atacama Desert with the meteorites. They look like this. So it can be just a recent falls where you can see still the fusion crust. But this looks like a new fall. The one that it's 22,000 years looks very similar to things that are just fall. So it can really preserve in a very good condition. And when they get older, they start to crack and start to create fillings with salts and sediments, and finally can break and generate this, where I am? I don't know, here. So they can break and become a part of the regolith of the desert. other things that we try to do when we look for meteorites, it's to use sieves. Take this is one square meter sample of sand that we sieve after we use magnetic separator. So we take all the magnetic separation and we process it in the lab. And after we use the stereoscopic loop to try to look for these micrometeorites, because it's also the flux of extraterrestrial material in other size, and that has it's very different, the composition of the flux in this size. For instance, we can find more carbonaceous chondrites and carbonaceous material that has more organics than the carbonaceous chondrite that we, most of the time, we just study that kind of samples for organic matter. So that were, in that site, it were 2,450 micrometeorites. In the same space in Tunisia, our collaborators found just 200. So Atacama keeps this, the record of this material in a very good shape for a long time as well. Other things that have been very significant, just because we walk the desert, is the finding, for instance, of these tektites that are the ejecta, the melt glass of the ejecta in an impact that travels and get this aerodynamic shape. So we were probably 7 years going to the desert. We found 23,000 samples that were completely analyzed to do the statistic of the distribution, the mass distribution in the area. And also the datations. So the glasses were around 8 million years. So in Atacama, 8 million years. There is a lot of explosion, like pyroclastic flows and things that can cover the structure. So we were looking for the structure. We never found it. This red here, it's the proposal of, I don't know if group Czech. You remember? I'm not sure, a Czech group that proposed that the crater was inside the strewn field of the tektites. We went there and it doesn't look like a crater. And the funny thing is that they don't behave like a proper tektite. So has a good morphologies, water contact. Appears lechatellurite, lack of relic grains, but also has characteristic of impact glasses with high impactor content. So we know that it's an iron meteorite, the one that hit and create this tektite field. Chemical heterogeneity, and also some lower temperature samples. So we are still searching for the crater. This is a work of Gabriel Pinto that will be with us next week with the updated new high density meteorite areas that has the name of just the geographic map, these areas. So as you see, appear a lot of different new ones more in the side of the closer to the Precordillera. Calama, it's a very big place where many of the private collectors have gone. And we never thought to go there because we know that every summer we have the monsoon coming from the Amazonas. So we were, no, meteorites will never be there. And well, it's a lot of meteorites there. It has a very high density as well. So also it's something that it's happening, like learning more about the surface of the desert because the meteorites have very good record to understand also the climatic changes in the time they have been spent in the surface. So we have been doing a lot of classifications. We have just one microprobe that most of the time is not working. So we develop different ways to try to get to the classification using other methods like magnetic susceptibility and also WebScam. And for a long time, we were just classifying like this, but now in the new repository that I will mention after, they calibrate the SEM to have these values to classify ordinary chondrites, that it's done with the values of phyllite and ferrocylite in olivines and pyroxenes, respectively. Also, we have one student that it's using the meteorites of Atacama to improve the database of opacities and all other parameters to improve the understanding of the signals that we receive from ALMA of the different planetary disk. So this is a recent paper of her PhD that we hope that we will continue improving this data set to know better the conditions in different parts of the planetary disk. And well, this is part of what we do. We have a network of different labs to analyze the meteorites in Antofagasta, Valdivia, Concepción, and Santiago. So most of them has the basic things to do the sample preparation, but other techniques, we just go and visit friends to do the classification and after to continue also to train new students. So part of this is what we have been doing with this magnetic susceptibility. Of course, the petrographic study that is very important, electronic microscopy, QuemScan or microprobe, also XRD, fluid inclusion analysis, infrared and Raman spectroscopy, Mossbauer spectroscopy, and geochemical studies that help us to understand some primary processes like condensation, accretion, secondary as aqueous alteration, thermal metamorphism, and shock metamorphism as well. And what happened also on Earth, that it's the weathering patterns of the samples. That is the new repository in Valdivia, in the Universidad Austral de Chile. So it's growing, and it's the first time we can really have a place well kept with good conditions that meteorites will not disappear or destroy. Where now we can keep the mass of the specimen samples of, so we are now trying to take it with the law that make everybody that comes to Chile to look for meteorites to let the specimen type in this repository. And Kevin is part of this repository. And so that is what we have been, the image of Gabriel Pinto. It's only this area where everybody has been looking because these are the very old surfaces. We have had some attempts in the south, in the Atacama region, and also in the Iquique and Arica region. And they look very like sometimes similar, but we walk, and we don't find anything. So we still don't know. We suppose that it's younger surfaces, but visually looks very similar to the ones of the Antofagasta region. So we are trying to understand better as well the behavior of this. And well, it's in our plans to can have an expedition to Antarctica to find meteorites. For that, well, I have been in Antarctica twice, but not looking for meteorites. But Gabriel, that will be here, he was in a meteorite expedition in the other side of Antarctica. So the Chilean bases are here, and the Belgium bases are here. So he got this experience, and the idea is to go there and find some meteorites as well. So these are just pictures of the 2025 expeditions. I was training a Mexican interchange PhD student because he wants to look for meteorites in Sonora Desert, but with guards and everything because it's more dangerous than here, that you really have the perfect desert to look for meteorites. Very, very nice. So in this case, we found multiple faults. That was not very common to find that. So we spent a lot of time. Well, that is the second that we went there. We also did a micrometeorite search, and that are the points of these different fragments of the same fault that we were studying, how they look, and the micrometeorite search. So that we found 3 dispersion ellipses, and also we went to check the crater that was proposed, but Hutskova, not finding anything. So this is how it looks, the crater. So it doesn't look like a crater. So we are still hoping to be able to use geophysics maybe to try to find the crater. That it's images of the glasses, how they look. And you can see the white stuff. I don't know, what is the... Okay, well, there. The white stuff is the iron meteorite that it's embedded in the glass. And finally, just in the beginning, before coming to Spain, we were with Kevin and my other students invited by the Natural History Museum project, No Shade, that it's studying they are drilling in the bottom of the Monturaqui crater, that it's a 600,000 years crater, very well preserved. But already there is nothing left of the impact material because many expeditions, scientific and non-scientific, has taken. So that it's also something like a geo-heritage thing that we need to try to protect that crater, create the way to not make the cars to go inside, and to give information to the people that arrive there that it's a very hard place to arrive, and has a very nice view of the southern part of the Atacama Salar and the Andes here. So that it's a big group that we were from every discipline that will be in the next year studying with different techniques the Monturaqui crater. So some samples that we found, we were lucky to find some samples of the impactites, and that it's my undergraduate student that will see effects in the granite of the deformation features that we can find in the under the microscope, and also the ignimbrite that covers all this area. So finally, just to say, Kevin is here, so probably you can invite him to give a talk about what is he doing: petrological characterization, thermal evolution, and abundance of soluble organic matter of thermally altered CO carbonaceous chondrites found in the Atacama Desert. So we have all those meteorites here, so you can go and talk to learn more about this. And Camila, my other student, it's doing the terrestrial biological colonization and weathering process in meteorites from the Atacama Desert in different spots. So it's also comparing the different climatic onsets that the meteorites have had. And so far, so not like geologists, we sample very bad, for biologists want to kill us. So a biologist teach us how to sample the soil, the meteorite, to have not so bad results. And so some of the primary results, now she's preparing the first paper of her PhD. And just the funny things that we do at So that is the artisanal way to make them good to after take the different sizes. So most of the micrometeorites we found it in the between 500 microns and 1 millimeter. And that are part of the few that we found in one sample with a very nice textures that we can find. These are the magnetites and olivines that we want. And just to finish, what we are trying to do, this year, we have been, I think, 15 or 20 years. This is the fourth proposal to protect the meteorites in Chile. Now we have advanced a lot, but we are almost to change government. And every time we have a change of government, everything falls apart. And we have to start from scratch next government period. So we are hoping that something is left with the diputados and senadores to not start from zero. And an invitation for all of you that we will be the place for the 2028 Meteoritical Society meeting in Antofagasta. And the idea is to have, of course, in this the normal topics that we cover in this kind of conference, but some science coming from local studies related with Atacama and everything, because I think it's an important opportunity to attract more students to this kind of science that we love, and to show what we can do from the Atacama Desert. So with that, I will finish, and muchas gracias.
Muchas gracias, Millarca. We have time for maybe a couple quick questions. It was such an amazing talk.
Hi, thank you very much for the talk. I really enjoyed it. So when you have a meteorite, but you don't know what you know, but I don't know, that it looks very similar to a rock. How do you know that is a meteorite? So you collect all of them, go to the laboratory, or you do the decision on site?
Yeah.
What are the criteria you use when they're very similar?
In the beginning, as we didn't know really how they look, we were with the pockets full of rocks, and after back pain. But after we realized, well, things that I learned looking in books and things, a lot of things look black. And the meteorites in the desert are not black, just if they fall very recently. So the normal color that we found in Atacama, it's brown, like a chocolate brown, from milky chocolate to dark chocolate color. So the color is very impressive. Among the other rocks, looks very like a shiny, because the metal of the chondrites make them have an appearance that it's more bright, and also nothing is like flat surfaces. It's very smooth, because it's the only rock that flow in the sky. So it creates this fusion crust that it's only 1 millimeter, just a little fusion in the surface that creates the same, I don't know how to explain, but it's like I don't know if you say fondant to these things that you cover the cakes, that it's very soft. So you can see, and also you see like somebody put the fingers in something that was soft, that we call it rec maglev. But sometimes that is another criteria. But sometimes in the desert, the wind can create the same appearance. So our brain computes like many different, like the color, the shape, the size among the other rocks around. And we say that this is a good candidate. We go there, and we go with a magnetic susceptibilimeter because the magnetics are like 10 times more than magnetic things on Earth. So, and we don't use magnets because part of our team study the paleomagnetic fields of these parent bodies. So we use the magnetic susceptibilimeter. And yeah, now I think just a few are we take it and we find out that it's a terrestrial rock. And now we are very, very good, more efficient to find the real meteorites.
Okay, very interesting. Congratulations.
Yeah, I have some samples here. It's not the meteorite, it's the ones that I cut to ring here. So the ones that want to see how they look, you can come after.
Thank you. If anyone else has just one last, I think you're going to have to fight. Sí, hay tiempo, hay tiempo. There's time.
Thank you. Millarca, which are the techniques to date the meteorites, and how do you distinguish which is the age of falling on the Earth or any other thing, formation or separation from the mother rock or mother meteorite, whatever?
Mm-hmm. Yeah, so for terrestrial ages, we use cosmogenic radioisotopes. So in the beginning in my PhD, because of the literature was done for other hot deserts, they were using carbon-14 because the age of the meteorite, the terrestrial age, was I think the average was around 12,000. So the carbon-14 works well for 14,000 or 20,000 until 50,000. But in my samples, many of my meteorites were like with zero carbon-14 because they were older than the technique. So the next that comes after me start to use chlorine-36. So now it's the standard protocol for terrestrial ages for Atacama Desert is the chlorine-36. And with that, we can cover the amount, like more than 5 million years. If we found one, the older that we have found, it's 3.8, I think, million years. So, and that it's a huge, opening of the window of hot desert meteorites for study the flux in this range of time. And it has been also very interesting for the ones that study paleoclimate because we have gaps of absolute no records that can be understand on how was the climate in those periods. So now the proposal of the thesis of Camila is using these meteorites to try to understand better the change of the climate because meteorites can record where it was a humid period or not. So it's a new proxy to paleoclimate as well.
Thank you for the nice talk. In your talk, you showed a map with the different populations of the meteorites collected, and there were clusters, no? There was an iron cluster. How do you explain those clusters? Is because there was like a bigger object raining down and then populating those areas?
We think are the little ones that we found in 2025, these multiple folds that were just meters. So most of the time we are not able to see the length of the ellipse. So what we need to try to see first the classification. So most of the flux is nominated for homogenic composition meteorites, but we have seen some little, not too many examples of meteorites that are like a rubble pile. of different kind of meteorites. So we never know that if we are in the just the exception of this heterogeneous composition meteorite that can fall, can break in the atmosphere, fall. It's the same fall, but we will find different meteorites. The most common is that this break will make the same meteorite in the field. So we need to go through all these analysis to try to see all the criteria to say it's the same. But the more strongest is the classification, but also the age. And for that reason, we try to correlate to get a sample that it's enough to be reliable to check the ages of these different groups that look similar. So that is the way. So in this case, Catalina used a program that was used in the beginning for detecting craters. So she used the same algorithm to try to find which meteorites were also generating a cluster that could be same form.
And if I can I ask another question? Yes, a quick one. And then, so regarding the aging or the age of the different meteorites, so in those areas where you only detect these relatively young meteorites, is it because the terrain or the area has been processed by the Earth, so that's why you don't find old meteorites, or what is the reason for only finding young meteorites?
No, we have the range between 0 and 3 million, 3.8 million. And the average in some of we don't have yet the full study of full Atacama, but we study the dense collection areas that have the same like climate, the same tectonics and everything, like what it's fixed. So we just analyze the same meteorites of the same area or the same behavior. So in them we can find then this whole spectrum of ages. In some surfaces that looks just the same, like the ones that have a lot of meteorites, don't have any meteorite. So we still are trying to understand the processes of the geomorphological processes, because we think are like patches of very old surfaces among others that are not so old. So, and in this very old, we can see this living together, the ones that fall yesterday with the ones that fall 3 million years ago. And that it's an unusual behavior for meteorites because as they are, all the composition was created without oxygen outside the Earth. They react very quickly to the oxygen. Also more if it's wet conditions. So for that reason, I think they preserve very well in hot deserts and cold deserts. But they need this like a hyperarid environment and stability, because earthquakes and things that happen also can disturb the surface. So we are like having a lot of information, trying to understand how meteorites behave. In other deserts, there is a correlation between the age of the meteorite and the weathering rate, but in Atacama, we don't see that. So we can find very weathered, young, like a recently fall meteorites, and others that are 1 million year that looks like with a weathering rate like it's 2, like a normal weathering rate, not for something so old. So we think also it's important other parameters internal to the meteorite, like the porosity when they fall, and also when they fall, if it's a humid or a dry period. Because if it's a humid period and the meteorite is more porous, will react quickly and probably will fix weathering, a high weathering rate in very few years. And after, when all the minerals stabilize for the environment, will stop this weathering and will like seal the meteorite. So it's very, we're still trying to understand what happened, because they behave a little different from other hot deserts.
Thank you so much, Millarca. And thank you for the talk. Sure.
Can I ask a very
Nice to meet you.
short question? Sorry, it's just
¿Dónde están hablando? Aquí.
yes. Thank you for your nice talk. You mentioned that you found some very tiny grains of carbonaceous chondrites. And if I understood correctly, the composition is different from the regular carbonaceous chondrites that you usually.
Yeah, we haven't found yet micrometeorites with a carbonaceous composition. We have this 19 that I show you is the only ones that we have found so far. But in the literature, other groups that have been studying them, they have found that mainly in places where they can last, because carbonaceous chondrites are also very fragile and can react more easily than others. So most of the evidence comes from the micrometeorites that have been found in the Antarctic or the Arctic pole. So they have been like melting the ice, finding all the dust. And after, with that dust, they go to see the stereo microscope, and they have found this material, and doing the statistic of this, a lot of dust particles, they have found that different than in other areas, the most of these micrometeorites come with this percentage of carbonaceous chondrite type of composition. That the ones that study meteorites, we know that when we try to correlate the amounts of meteorites that we found with the amounts of asteroids of the same time, they differ a lot. So the C-type asteroid.
But differ because the alteration, or differ because it's a different kind of
No,
classification?
we were thinking that the carbonaceous chondrite that are the most representative in the asteroid belt, maybe because of the fragility, when it comes to hit the atmosphere, probably breaks more and don't finish like a proper meteorite that will last. So it probably sparse in the atmosphere. And for that reason, we see, because it's only 5% of the full collections of meteorites, the ones that represent the carbonaceous chondrite, but it's very different in this size. In this size, it's more of this kind of meteorite. So it's like when you are tiny, maybe you don't melt, or so you can last as a micrometeorite. So that is at least for my perspective, I would like to go to Antarctica and do this and try to find these micrometeorites there, because what we found in the Atacama are olivines and more chondritic, like ordinary chondrites. So part of the team looking for the meteorites, but I would like to be with a team that will be melting ice, because I think can have a lot of interesting information, this part of the flux that we don't see too much, because it's very hard to work with micrometeorites.
Very interesting. Thank you.
You're welcome. Ahora sí. Voy a sacar unas fotos, no se vayan. Voy a contar que sí hubo gente.
Muchas gracias, Millarca.
Muchas gracias a todos. Hola, ¿qué tal? Mucho gusto.